Good morning. What an honor to do the first presentation. But then on the other hand, Janus, my coworker, is going to present right after me. So I don't know, I feel also like I'm warming up for him. Yeah, and how do I? Yeah, so my name is Nis, and I work at Unity, the game engine company in the audio team. So I'm going to do a presentation on aliasing. And yeah, there's different definitions. We're going to go with the mathematical one today. And we're going to focusing on aliasing in audio. So yeah, there's both aliasing in video and audio and different domains. So one example in video could be like if you watch a movie, you watch the wheel, when it starts spinning, suddenly it looks like it slows down and then goes backwards. So that's because the frame rate of the camera cannot catch up with the speed of the wheel. And yeah, you also have in video, like if you're a graphics designer and you resize your image without low pass filtering, you also see these like weird artifacts. That's also aliasing. And in audio, of course, which is what we will focus on today, you can hear it as weird artifacts when you have harmonics that are higher than the Nyquist radio. So just, yeah, a quick example of aliasing in video. And for audio, so here we have a square wave naively generated. So all the crap you can hear at the high end of when it sweeps up, that's the aliasing. And here is the same square wave, but with the aliasing suppressed by the methods that we're going to go over today. Yeah. So some people like the sound of aliasing for nostalgic reasons, but so why do square, saw, triangle, geometric waveforms, why do they alias? So it's because, in a sampled system, you can only represent frequencies up to half the Nyquist rate. Anything above that will fold back. I'll show an image of what that looks like in a minute. And saw, square, and triangle waves, they have discontinuities. And whenever you have a discontinuity in a waveform, when you try to sample it, it will generate an infinite amount of harmonics and they will fold back. So this is like an example of a naive square wave. You just take the Fourier transform, and then we can see as we zoom in vertically, we can see the harmonics are like folding. The higher harmonics are like folding back and forth, like. So basically, that's what you're hearing as we're sweeping up. Then you can hear all these like harmonics above Nyquist folding back. So how do you get rid of those higher harmonics? So the classical way to do it is to synthesize your image or your audio at a super high sample rate, and then you low pass filter, and then you can downsample and decimate. So that's expensive to do if you want to do it for oscillators, because you have to oversample a lot and then low pass filter, and that's quite expensive to do. So yeah, the BLEP and BLAMP approach instead is about you go in and then you correct the signal at the discontinuities before you sample it, seen from mathematical point of view at least, and then you sample it after that, and then the aliasing should be suppressed. So what is BLEP, BLAMP, BLAMP? Sounds very nerdy. So it's band-limited impulse, band-limited step, and band-limited ramp. And how do they relate to each other? So the blip is just a direct impulse. I'll show that in a diagram in a minute. That you have low-pass filter. And then then you get the blip by integrating the bleep, and then you get the blamp by integrating the blip. So yeah, I didn't came up with these words. So you see here the top left corner, that's the impulse function. And then you integrate that one, then you get the step function, and you integrate the step function, you get the ramp function. And then the same for the blip, BLEP, BLAMP. So the blip you get by band limiting the impulse function. And so when you take the impulse function and you go to the frequency domain, the direct function, it has like unit frequency response. So then you just low-pass filter that, and then you end up with a rectangle. And then when you Fourier transform that and go back to the time domain, then you'll have this like blip, which is just like a sinc function. And then you can integrate the sinc function, go to the blip, and then you go from the blip to the blamp. So yeah, this is very important for the rest of the presentation to understand this relation. Okay, so how do we use them to correct a signal? So first we need to compute the residual of the blip and blamp. And the residual is really just, you take for the blip, you take the step function and subtract it from the blip. And then you get the difference, you can say, between the blip and the step function. So then you just get like the wobbles only. And the same thing for the blamp. And then you have your naive square wave in this example. It could also be a saw wave or a triangle or whatever geometric waveform you can come up with. Then you go in and then you manually insert the blip whenever there's a step, the blip residual whenever there's a step, and then you get this, then now this one will be like a band-limited square wave, and then you can sample it, and then the aliasing will be gone. So next problem. So both the blip, BLEP, and BLAMP, they are infinitely long in both directions. So typically what you do is you need to window it, and then either you can store it in tables and interpolate between those tables at runtime when you need to insert it at the discontinuities, or you can approximate them with a polynomial, which is what we're going to focus on in this presentation. So now we are arriving at the point where this is the point of this presentation, because I understood blip and blamp in the past, how it works, but I never understood how to derive the polynomials. And when you look at the math papers, I at least have always thought it was like quite baffling. So I tried to see if I can simplify it and cut to the chase in 20 minutes. And it's a quite complex topic. So anyway, what spline should we use? So the sinc function, which is really what we are trying to approximate with the polynomial, is known as, you can say, the ideal interpolator. So it's like if you want to do the perfect interpolation between points, then you use the sinc function for that. So we need to find something that approximates the sinc function. Okay, so when you do interpolation, like maybe if you work with video, you know the Catmull-Rom spline is very good for interpolating between points. So we could try and start with that one. And I've shown the math here for how you derive the Catmull-Rom, but it's not really important. But I just included it here for completeness if you want to look at the slides later. So basically you derive this Catmull-Rom spline, and you can see it looks already starts to resemble a sinc for the cubic version. And the cool thing is you can add even more constraints. So the way you derive it here is you have these constraints to set up, and then you can derive the Catmull-Rom matrix, and you can go up even higher. You can go 6 points, 8 points, 10 points, 12 points, and add more and more constraints. And the more constraints you add, the closer this one will get to, it will converge to a sinc function if you added infinitely many constraints. That's pretty cool. B-splines, which is also a popular polynomial for PolyBLEP and PolyBLAMP, they'll converge to a Gaussian distribution instead. So yeah, something cool property of those two families of splines. But we'll go with the Catmull-Rom cubic Hermite because that's more mathematically nice, and that one converges to the sinc. So next thing is now we have this derived, this Catmull-Rom, then we integrate it to get the PolyBLEP. And the integration can actually be expressed as a matrix multiplication. So you just take the Catmull-Rom and multiply it with this integration matrix, and then you get the BLEP. And then you can do the same thing again with the BLEP, and then you get the BLAMP. And that's, you also need to adjust the segments a bit afterwards, but that can also be represented as a matrix. So actually you can do just matrix operations to derive them, which is really cool. So you get the PolyBLEP, and it also resembles the real BLEP function, and you can go to the BLAMP. So here is an example of a saw wave that we show the harmonic spectrum of it with no suppression, and we can see here there's a lot of noise. And then when you analyze it with the cubic Catmull-Rom, then you suppress a lot of that aliasing. It's not perfect, but it's, as you heard in this audio demo earlier, it's quite effective. Okay, so I included this code here. So it's a lot of code for one slide, but my idea is that hopefully someone will watch this in the stream and screenshot it, and then they will go in manually and type the code in like you did with those magazines back in the old days. Then you type in the program and then run it on your Commodore 64. So this is like completely self-contained example. So if you put this in your C compiler, it will run and spit out floats on the std out. So it would have been cool if it could have, if I could have generated a wave file, but I couldn't fit that in one slide. So you have to do that yourself. But yeah, it's a fully functional anti-aliased oscillator. So just quickly, if we look at the code here, we have this process function. That's the important one. We start with computing the delta, which is how far we move each sample. It's determined on the frequency of the oscillator. Then the first thing for each frame, the first thing we do is we just compute the naive waveform and put that in the window. We have a running window of 4 samples. That's important. Okay, then we need to now sweep over the delta and look for where the discontinuities are. And there can be multiple discontinuities in one delta if you have a complicated geometric waveform. So we need to sweep over. And then so as we sweep over, we look at, okay, where is the next edge in the future? How far out is it from where we are now? And then if that edge is within the distance we're sweeping, then cool. Then we are gonna add a blip at the edge. If it's not, then all the future edges are outside the current window, and then we're just done, and we go to the next frame. So if it's within reach, then we need to compute this delay that we need to, so the subsample within the sample we're looking at, where is the edge? We need to compute that, and then we can use that to feed to this add blep function, which will apply the blip on the window given the delay. So it will time shift the polynomial, so it will be placed exactly with the middle of the polynomial at the middle of where the edge is. And then we just do that until there are no more edges, and then we continue with the next frame. And then when we're done, we fetch from the front of the window the next sample, and then we slide the whole window. So we take all the samples and move, and then put in a 0. So now we're ready for the next frame. And then we do that for each frame. We need to compute it. And yeah, up here, that's the BLEP polynomial we derived in the earlier slides. And yeah, I think that's it. So takeaways. Aliasing in virtual analog oscillators arises because of discontinuities. So we fix locally by adding a small polynomial residual at the discontinuities. We use BLEPs for steps and BLAMP for slopes. And I didn't have time to cover slopes in this presentation, but it's the same thing whenever you have like a discontinuity and not a step, but you have a discontinuity in the derivative, then you use the BLAMP instead. Exact same thing. And then you derive them by integrating, so you already covered. And then you can do this for frequencies up to Nyquist. Above that, you should use oversampling. Thank you. And I'm gonna have an open source implementation up at this address at some time in the future. I didn't manage to get it ready for today. And we have 10 seconds left. So we can just take 10 seconds of silence before Janus gets on. Thank you.